Welcome everyone to the Departmental Seminar of the Department of Condensed Matter and Material Physics. It's a pleasure to have an alumni of this center to give the departmental seminar. So we have Dr. Poulami Chakraborty. So Poulami did her PhD at the Bose National Center for Basic Sciences with Professor Shahadas Gupta. Then she moved on to do her postdoc at the Max Planck Institute for Eisenforschung in Düsseldorf. Currently, she is associated with both Max Planck as well as Basque Center for Applied Mathematics in Spain. And today she is going to talk about interplay of hydrogen with defects in aluminium alloys. So we welcome Poulami. Thank you.
Thank you. I don't know your name.
Saket Shami.
Okay. Thank you, Dr. Shami,
Yes.
for the nice introduction. So, as you said that I am coming here after 5 years, and it's my pleasure, and I thank everybody for arranging this seminar and giving me the chance to speak on my very recent work, which I'm excited to share with you all. So, my recent work is on the effects of hydrogen with defects, specifically in aluminium alloys. Before that, I would like to briefly introduce the topic of hydrogen embrittlement. So by the word hydrogen embrittlement, what we understand is in presence of hydrogen, we know that there are various degradation mechanisms which happen due to its presence in the environment, and because of which there are various problems seen, or a lack or a loss of the mechanical properties in the alloys, in metallic alloys specifically, and that is what we want to talk about today. So here it is a typical stress strain diagram, and this one is our engineering stress strain diagram. And here you can see the blue and the red curve, they are significantly different. Why they are different? The blue curve shows that here it is a prototypical aluminium alloy, which is not electrochemically charged, and this one, the red one, when it is exposed to hydrogen through electrochemical charging. And as you can see, there is a sharp decline in the ductility of the alloy in the presence of charging, and that is our focus. That is why we want to study about hydrogen embrittlement, because it decreases the mechanical properties and affects it so strongly. Before we move on to our study, let us give a brief introduction. So this is a typical schematic diagram where we see that a typical surface. This is the surface of a material, the surface of alloy, you may presume, and it is exposed to hydrogen or water, whatever contains hydrogen gas or in the water form. And because of its exposure to this, the surface, from the surface it starts ingressing inside the material, and it causes various types of defects in the form of point defects, vacancies, precipitates vacancies. It also forms crack, and various types of dislocation are shown in here. And that is why this is all of a sudden and that is why this is such a interesting study, and this is a wide field to study. The most popular mechanisms in literature are these following: help hydrogen enhance localized plasticity, which mostly means that in presence of hydrogen, how the local environment is modified, and there is a yes, and the local plasticity mechanism is introduced. Here it talks about mostly in presence of hydrogen, how it promotes decohesion, and this talks about the presence of hydrogen promoting strain-induced vacancies. Even though there have been several studies in literature regarding these various mechanisms, and people have been trying to explain this, but there is a very little understanding in the mechanical and the chemical aspect, because these are coupled mechanisms and very complex in structure. Therefore, motivated by that, my focus of my present study is hydrogen trapping and diffusion in materials, in metallic alloys, and their interactions with various other constituent elements which are mostly present in alloys in nature. and the damage which is induced because of the presence of hydrogen and how we can tackle that. Okay, having said that, I will first give you a ride through the first three specific cases, because these three specific cases are forms the important areas where we focused in our present research work. First case being the hydrogen and grain boundary interaction. First, let us see what is the grain boundary. So, this is a typical schematic diagram, and let us think that this is a sample. This is a sample. It can be any alloy or any kind of a sample, material sample. And here you can see there are various lines, and this represents various textures. So we know that in a sample, in a crystal, or in a material, there are various types of different. If you focus onto it, each of it can be divided into various different orientations. Like you can divide it into various grains. You can call this grain 1, grain 2, grain 3. They can be differentiated on the basis of the way they are oriented, as well as on the basis of the way their texture is. Now these purple dots show the constituent elements. In nature, you wouldn't find, mostly you wouldn't find a pure element as it is. There is always defect, and defects are present in the form of maybe in very less form or sometimes in much more form, but in some weight atomic percentage of other constituent elements. So let us call these solute atoms, and these are solute atoms present in this material. Therefore, since these two grains, suppose this is grain 1 and grain 2, these two grains, this part is, we can call it a grain boundary. Now we will focus at the grain boundary. So here there are two types of grains with different kind of orientations or texture, and we have two solute atoms mixed in it in the normal form. Generally, we see that they have a tendency to segregate at the grain boundary, because at the grain boundary, due to different types of orientations and stress, there is a misfit strain accumulated, because of which there is the interface becomes much more important, and interesting mechanisms happen there. One of them is segregation to the grain boundary, and they like to sit there. Now what happens if there is hydrogen present in the vicinity? Sometimes we see this mechanism that hydrogen being present in the vicinity, it would like to form a free surface. This is what we call a free surface. That is, it doesn't want to be in the grain boundary form, but it is much more happier, and the energetics is much more lower being at the free surface. Having been said this, as you can see, this is a experimental picture taken from this reference, where they show that the crack is initiated by hydrogen enhanced equation, that is the HEDE mechanism we were talking before. Here there is a crack formation, and they have seen that after introduction or electrochemically charging the material over a long time, this crack is being formed. Now coming to another case, let us assume that these solute clusters are these solute atoms are dissolved in a solid solution. Then they come together and form solute clusters, which happen a lot of the times. But we will be focusing on this grain boundary again, and we are seeing that there is a depletion of solute atoms therefore here, because the solute atoms have formed a cluster somewhere else, far from the grain boundary. Now, if we see that there are hydrogen atoms in the vicinity, this is another case which shows that in presence of hydrogen, it is also wanting to go and sit at the free surface, but without the effect of solute atoms here. The last case being, what if we try to see this interface of this solute cluster and the grain? So it is something like this. And then the interaction of hydrogen with the precipitate. And these solute clusters are mostly called precipitate, and these type of interactions are mostly comes under the study of hydrogen precipitate interaction.
Maybe I came in late, so hydrogen is there in the preparation. Why is there so much hydrogen?
we are talking about electrochemically charged sample. That's so what happens when hydrogen is already there? Because as okay, let me just yes, yeah, here. So we have taken two samples. The blue sample, which is uncharged, and the red sample, which is charged hydrogen. So in the charged hydrogen, since there is a drop of ductility, drop of ductility. The question is, are they intentionally charged? They are intentionally charged in order to understand that in chemical environment where there is hydrogen already present, either in the gaseous form or in the water form, what happens and how these cracks are initiated in order to study the mechanisms. So in the experiment, it is initially charged electrochemically, intentionally. Okay, sorry, I will go. Okay, yes, and this is a this diagram is being taken. This image is being taken. This APT image is being taken from this paper, which actually shows. You see that the purple dots are the titanium, green at the carbon, and pink is deuterium. You will see a lot of pink dots here. See the it's circular and it is dissolved everywhere, and this is the first time. It is, I think, 2010. It is the first time that they have been able to visualize hydrogen in experiment, because it is extremely difficult to visualize hydrogen. And why we are interested in such kind of study is because hydrogen has due to the small size of the hydrogen and its high mobility, it easily diffuses into the materials, and there are a lot of complex mechanisms, and it is extremely difficult to detect them experimentally. As you can see, this is the first detection which was reported by Takahashi's paper, and where they have shown a spatial decomposition of the elements, various elements, and this is also electrochemically charged sample where they have been able to detect the hydrogen here. Deuterium? It is deuterium, and deuterium is actually used more commonly than hydrogen because of its atomic mass being heavier than hydrogen. So therefore, whenever you are trying to measure the hydrogen content, there are sometimes in the atmosphere you have hydrogen, and therefore you cannot differ. It is difficult to differentiate the composition in the atmosphere, in the experimental atmosphere, and in the sample. So if you take deuterium, you can differentiate it because of the atomic weight. Now I will come to my research topic, which is about aluminium alloys, and why I was specifically interested in aluminium alloys. As you can see from the bar diagram, throughout the last 30-40 years, there has been a sharp increase, and it is increasing even more so because of its increased industrial use. Firstly, it was mostly used in the aviation industry traditionally, and now it has found its use in the day-to-day life, specifically in the automobile industry, and therefore it is extremely important as an industrial material, and it serves, an aluminium alloy serves as the structural components of various such industrial elements. So we are focused on the 7XXX aluminium alloys because this aluminium engineering aluminium alloys are used in the aviation industry because of its high strength, load. I will come to that. High strength, low density, but it is highly susceptible to hydrogen embrittlement. So what is 7XXX? So the XXX is nothing but this constituent element, zinc, magnesium, and copper. And the number seven is the engineering contest because they have come up with 2, 3, 4, 5, and this is it shows the strength. The highest strength now they have come up with is 7XXX. I think the next one will be 8 something. So yeah. As you can see here, from the weight percentage, the major constituent elements are zinc, magnesium, and copper, which is important to note here, because they will be playing an important role with the interactions in our hydrogen study. So as I have introduced, as I have discussed before, that hydrogen diffusion is very difficult to study, and therefore a hydrogen diffusion and trapping in aluminium alloys is what we want to discuss about. And I will start the discussion with this beautiful image created by my colleague Huan Zhao. Here, this image is a electron backscattering image, where you see that the 7XX aluminium alloy, which I have just now introduced, that alloy is being electrochemically charged for enough long time so that there is an intergranular crack being formed. It is being electrochemically charged, sorry, and also there is a uniaxial strain being applied along it so that there is an intergranular crack being formed at the surface. Now we focus on the intergranular crack. So this crack is important because the microstructural evolution around this crack surface is what we are mostly interested. So as you see that it is numbered, this is some kind of a distorted structure which they have denoted as dispersoid, grain boundaries and intermetallics. So seeing it in detailed structure, we see that number one is aluminium C zirconium dispersoid. Why it is a dispersoid? Because it is a deformed defect structure of aluminium C zirconium. It is not ordered one. Then in the intermetallics, there are typical S phase secondary. S phase means secondary phase particles being formed. Here it is typically aluminium to zinc magnesium. I will come to all this later on. And 3 is where the grain boundary is formed. And our focus today is on these 3 microstructural evolution. And how is
one zirconium percentage is very small. Whatever you are showing, 7 but still it forms. Zirconium is 0.15, but still it forms such a kind of a compound.
Yes. Still it forms such a kind of a compound. You may say that, that's a very good question. You may say that there is a clustering of the solute constituent zirconium elements with the aluminium, and they have formed this disordered alloy structure. And it plays an important role in the hydrogen interaction as well. We have put aluminium 3 zirconium, but it is that's why it is called dispersoid somehow. They have that's why it's called dispersoid. That maybe disorder would have made more sense.
But we don't have any copper because it's very common that aluminum copper is like structures. I mean, it's not your fault. It's like experimentally they don't find it.
Aluminium, zinc, magnesium. No, I didn't.
Aluminum, copper.
No, I had actually intermetallics with copper, but we have not looked into it in detail here. Because that is because the copper.
I mean, that will be probably a primary thing. I mean, this will be less common.
Aluminium 3 zirconium.
Aluminium copper.
Aluminum copper is very
Aluminium copper was not there. We didn't see aluminium copper actually. But there was secondary phase particles. In the secondary phase particles, there was precipitate form, and with that there were kind of 3 constituent elements. One was aluminium, zinc, magnesium. One was, I think, aluminium.
There is the 5 phase. Aluminium, zinc, magnesium is the 5 phase of.
Yes, yes, yes. But it had some traces of copper into it, but mostly zinc and magnesium. Okay. So therefore, our primary aim from here is atomic scale analysis of hydrogen and its interaction with the various evolution of microstructural features in the alloy. First, in order to start, I have done a solute hydrogen interaction in the bulk aluminium phase with various 3D elements, and you will say whether I have taken the solute elements very randomly. No, I didn't. These are the common solute elements which are mostly present in various types of aluminium alloys. And as you can see, there is a very interesting trend that can be seen here. So with increasing d electrons, the binding energy of the hydrogen and the aluminium in the bulk phase kind of decreases. And also for silicon and tin specifically, and also for zinc, the binding energy is coming to be positive. So that is a very interesting observation, which will also have some impact later on while I do the similar study in the grain boundaries. So for the grain boundary study, I have typically chosen a high angle grain boundary because high angle grain boundary are the mostly commonly found grain boundaries in such microstructure evolution. And the prototype, I have taken a prototype sigma 5, which is a symmetric tail grain boundary. And this is the simulation cell I have worked with, and the blue atoms are the aluminium atoms, and the green atom is the magnesium atom, and the red atoms are the hydrogen atoms. And this is the two grain boundaries. So I was all along talking about grain boundaries. As you can see, it is very simply seen here that it has different kind of orientations, grain orientations, and therefore it is a grain boundary here. And the grain boundary, there is a lot of free space, and the spacing and the atomic arrangement is very different. And therefore it becomes a very interesting place for interaction of various types of interactions. Okay, so focusing on this, one of the grain boundary, uh, this is nothing but the zoomed 3D type of image I have tried to create here with the numbering of the atoms, and from there the various polyhedral units where I have put, this is something where from the top of the paper you are seeing, but if you see it from a 3D angle, these are the polyhedral units which are formed, and I have taken these polyhedral units, and in each of them I have placed hydrogen once in presence of magnesium and studied the interactions. So let us see what exactly we are trying to study. Suppose there is a grain boundary, there is a solute element, magnesium here, and it is migrating to the grain boundary. Then there is diffused hydrogen, and it is also coming to the grain boundary. And after both of them are in the vicinity of each other, they are forming a free surface. So we are trying to evaluate this situation, energetics of this situation. So this,
What's this? Elliptical?
yes, all of these calculations are data calculations. Okay, so this blue part is corresponding to the hydrogen. This is the segregation energy of hydrogen, and segregation energy of hydrogen means if these two blocks, if there is hydrogen and it migrates to the grain boundary, what is the tendency of the hydrogen, or what is the probability that the hydrogen will go and sit at these interstitial sites? These interstitial sites are named here. And similarly, this is the segregation energy of hydrogen in presence of magnesium. That is, if now magnesium is already present, and then we put hydrogen in presence of magnesium, whether how the effect changes. I will come to this to the definition of grain boundary segregation, how I have calculated. First, I would like you to know that E less than 0 here indicates that the hydrogen atom is happy. The more negativities, the more happier the hydrogen atom is to sit at the grain boundary instead of the bulk. That is, it will try and migrate to the grain boundary surface. This point is very important. Why this is a very important why this is a very important quantity, the segregation energy quantity? Because for the grain boundary energetics, it is a coupling of a mechanical as well as the chemical contribution. How? So there is a grain boundary, and we are removing the host atoms, because here there are no solid atoms. Okay, there are aluminium atoms, and now we remove the host atoms. So we create a vacancy there. Then we put uh, the substitutional structure. I mean, then we relax the atoms here, and here we put the substitutional atoms. So the substitutional atoms and the host atoms, the sizes are different. Therefore, when there will be this final structure where the solute elements will be moving there and replacing the host atoms, there will be chemical interactions as well as there will be mechanical contributions. So there will be a misfit of strain energy, and that is the most important aspect here. And this is how we are calculating. It is nothing but the energetics of the structure of B and difference of the energetics of the structure of B and difference of the energetics of the structure of A. That is how we are calculating the grain boundary segregation energy. Now we come to another very important concept. Sorry, I have forgotten to write it here. Eta is nothing but the embrittling energy, or it is also commonly called as the strengthening energy. This is the difference of segregation energy to segregation energy, as we have discussed just now, to two types of surfaces. One is grain boundary, one is free surface. I will show it in a moment. So the free surface is nothing but when the grain boundary is formed, and if there is another case where I have shown where the hydrogen is present and the solute element is present, and there is a crack formed. So that is the free surface. In this case, as you can see, the strengthening energy is the thermodynamic driving force. It is defined as a thermodynamic driving force, which shows that whether the presence of this particular solute elements or these defects will lead the system to will be happy to be at the grain boundary, or whether it will be happy to form a free surface. This is very important. Why this is important? Because this will definitely give us a knowledge or probability that whether this whole structure or this whole system will be driven to the free surface formation. However, there is one thing that is missing in this parameter. This parameter doesn't give you the difference, the what it is called, the energy gap, that the energy barrier that is needed to cross from this grain boundary to the free surface. That means that the energy barrier, if you want to go to the free surface, what is the energy barrier that you need to cross? That is not given here, but it definitely gives you the tendency or which surface makes you happy. So therefore, okay, let us focus first on these two plots. On this plot, this shows in present there is no hydrogen in the system and only magnesium is present, and we can see the segregation energy is negative. This negative segregation energy basically translates into this, that the magnesium in the aluminium sample.
So you have some minus
Yes.
on the axis.
Yes, sorry. I'm very sorry. Thank you for pointing it out. Okay, the segregation energy of magnesium is negative, and this implicates that magnesium stabilizes the aluminium. If there is pure aluminium and if there is a sample with magnesium, the magnesium presence of magnesium in the aluminium stabilizes the aluminium further. But this eta, which is the embrittlement factor or the strengthening mechanism, is very, very low. It's close to minus 0.02, which kind of says that it has almost no effect. That is, if magnesium is present, it wouldn't care whether it is at the grain boundary or it is at the free surface. Now coming to this diagram, you have already seen the lower plot. Now in each of these, so each of the hydrogen sites are also shown here, what it looks like, where it is present, and in each of these hydrogen sites, you will see this the top light blue color is the embrittlement factor. That is how much when the hydrogen goes to these segregates to these sites, what is the tendency or the probability of the hydrogen that it will prefer a free surface. Very interestingly, you can see that the sites which has highest segregation energy, or the sites where the hydrogen is happiest to sit, that is 2GB and tetrahedral sites, have also the highest embrittlement tendency. That is a very important point. And to top it all, this is the diagram which shows, this is the plot which shows the energetics of the segregation energy and the embrittlement energy of hydrogen in presence of magnesium. As you can see, in presence of magnesium, only the lower curve, if you can see that there is not much difference in presence of magnesium. The hydrogen segregates to the respective sites, maybe with a not very significant quantitative trend. But in the embrittlement tendency, the presence of magnesium enhances the embrittlement tendency when hydrogen goes and sits beside magnesium. This is further shown here in a comparison graph, where you can definitely see the differences. Therefore, the main take-home message from this from here is that there are two opposing effects. The two opposing effects being on one hand, magnesium is having no effect on the segregation of hydrogen. On the other hand, magnesium is having a huge effect and it is enhancing the degradation effect of hydrogen at free surfaces. Therefore, and we can safely say here that it favors grain boundary decohesion.
So how much is the chemistry effect instead of magnesium, sodium, calcium? I can understand. Magnesium has
The point is why we have started with magnesium, and in this particular grain boundary calculations, I will only talk about magnesium, because magnesium
No, I understand
was
that
seen in the experiment.
7xx
Mhm.
that thing has magnesium.
But I have not.
But if I have to understand it chemically, because
Oh
I
yes,
think
great. I am coming to that plot. I have a plot on this. I completely forgot. Yeah, what happens when other elements are put, obviously. Yes, the next slide comes to that. Yes, so the effect of other alloying elements on embrittling energy. So the effect of so these particular alloying elements have been chosen based on the bulk calculations. So I have included tin, and I have included scandium, zirconium, and magnesium. As you can see, magnesium is much lower in the embrittling energy curve, and zirconium and scandium is having a much more degrading effect in presence of hydrogen.
that's fine, but you know what is the reason? I mean, that's just an
Yes.
output of your
No.
calculation.
The reason being zirconium and scandium is known to have a very strong binding energy with hydrogen. And this okay, this each of these points has been calculated based on the segregation energy corresponding to each of these interstitial sites. But the segregation energies are highest in one or two sites only. So therefore, realistically, the segregation energies which is mostly negative, the hydrogen will have the tendency to go there. If we consider that case, we will have this second what to say, with second dotted, almost dotted lines of each of the corresponding elements, which typically shows the lower limit, where if it goes to the interstitial sites with the lowest segregation energy or highest probability where hydrogen might occupy, we end up with these energy plots, which doesn't change the trend. However, for the blue curve and the gray or the black curve, you see something interesting, right? The blue is corresponding to tin atoms, and the black curve is where there is no solid elements present. So we see that when we consider the lower limit of tin atoms, it is actually the embrittling energy is becoming much lower. It is an extremely interesting effect. Why? Because that means that the embrittling tendency is somehow decreased by the presence of tin. The embrittling tendency of hydrogen is somehow decreased in the presence of tin atoms. And the solute, this is also definitely because the tin is strongly binding with hydrogen, and it is becoming a trapping site for hydrogen. But also in the grain boundary, it is not increasing the embrittling tendency. The zirconium and the scandium is also strongly binding to hydrogen, but it is increasing their brittle tendency together. So you were asking about the chemical effect here. So this is the difference between the chemical effect. So coming back to the other precipitate and secondary phase materials, which we have seen in the experiment. The other secondary phase material, the S phase, is aluminium 2 copper magnesium, as you have inquired before, which was primarily C present, and aluminium 3 zirconium. And here in this plot, it is shown the concentration of hydrogen is shown and the solution enthalpy of hydrogen is shown. As you can see, the solution and solubility of hydrogen in aluminium 3 zirconium is seen to be very, very low, and the concentration is also very low. However, the concentration of hydrogen in aluminium 2 copper magnesium is much higher, and however, the solution enthalpy is much lower. So,
Y-axis.
yes, it is actually it is representing both of it. Y-axis. So these are the composition profiles we have obtained from the experiment. And in aluminium zirconium, however, contrary to what we have got, you see that aluminium zirconium and aluminium copper magnesium. So, let us focus on this blue hydrogen curve or the deuterium one. It is much more in aluminium zirconium. The hydrogen is trapped much more, the content of hydrogen, than what is trapped here. However, interestingly, the composition of deuterium is seen here, which is here it is the atomic composition is around 3 or something atomic percentage, which is kind of matching with the atomic concentration of what we have got from the DFT results. However, the lowest hydrogen solution enthalpy is also matching with the APT results, but the lowest hydrogen solution enthalpy is not matching with the APT results, and this is something we have come to realize, that in aluminium zirconium, hydrogen occupies octahedral sites. With zirconium at the secondary nearest neighbor shell. However, there can, because of the disorder in the structure, there can be zirconium antisites present in the first nearest neighbor near the hydrogen, which might be the cause of the increased hydrogen solution enthalpy as seen in the experiment. Now I will present how our theory is complying with experiment with the grain boundary structure. And as you can see, the grain boundary structure among all of these intermetallic phases and the distorted alloy system, the grain boundary has the least amount of hydrogen trapped in it. Therefore, from here we conclude that the intermetallic phases in bulk act as trapping sites for hydrogen. And we will discuss about the possible embrittlement mechanism. So throughout I have discussed the importance of the factor eta, which gives us the strengthening energy, or which gives us the quantity that the system will be driven to the free surface. So the more the larger the eta is, the larger is its probability that the system will be driven to a fracture, which can be seen highest for grain boundary and lowest for aluminium zirconium. And this complies with the experimental results as well. This implies that hydrogen is much more detrimental at grain boundaries rather than when it is in this trapped in these intermetallic phases. Because in that case, it acts as a trapping, it gets trapped in those sites, but it doesn't drive the system to a free surface. And in
other words, if you see any crack surface of aluminum, such as you shouldn't have any Al3 zirconium on the crack surface.
No, it is mostly near the grain boundaries. I have shown I will go to the picture maybe later on. the first picture which I started with, there near the intergranular crack, there was this grain boundary thing, absolutely adjacent. I will go to the after the talk. So therefore, we have come to this mechanism that how the whole thing might be happening. That hydrogen is entering into the system, but due to its higher solution enthalpy in the intermetallic phases, it is first choosing to be inside these intermetallic phases, then it is getting trapped somehow. Then the rest of the hydrogen is going to the grain boundaries. But once it is entering the grain boundaries and it is getting saturated there, the saturation of the hydrogen is leading to accumulation at grain boundaries, more and more hydrogen, which becomes more detrimental because once hydrogen goes there, even in lesser quantities, the presence of magnesium favors the grain boundary decohesion, and we can see grain boundaries much more near the crack formation regions. Therefore, our study provides indication that how we can increase such hydrogen trapping sites. Which are the solute elements which can increase hydrogen trapping sites, and which are the elements which needs to be avoided, and their respective tendency to initiate damage in hydrogen-induced degradation. So this can also lead suitable candidates and for materials design mechanism to improve the resistance to hydrogen embrittlement, and therefore that is the most important, and that makes it mostly significant. And this is the first ever time it was successful that our aluminium alloy was electrochemically charged with hydrogen, and hydrogen has been measured here in this particular work. And also we have been able to link up, not totally, but we have been able to provide some explanation from the DFT calculations. So, so this work can be summarized into this main message, that is hydrogen is detrimental if it goes to the grain boundaries, and alloying elements may be used to further manipulate the strengthening properties. This work has been published in the recent Nature paper with my colleague Zhao, who did all the experimental work, and I have done all the DFT calculations. So the whole focus of most of such work is how the precipitates, various type of such solid clusters form precipitates and they interact with the matrix at such interfaces, and whether it promotes grain boundary decohesion or whether it strengthens the grain boundaries, and how solid segregation plays a role, and in middle of that, what is the effect of hydrogen. So with this, I would say that we have almost come to the end of our talk, where the solute interaction and the competition between precipitate and grain boundaries have been presented here. And I hope I have been able to convince you that the impact of certain solutes on grain boundaries can be used as possible alloying elements, which may act as very important guide for such future experiments. My present and future research plan is mostly about such complex materials in real environments, which are mostly collaborated with such experiments, because no element or no metals or metallic alloys are without defects, and therefore defects form such an important part of our study. And in any chemical environment, whenever we use such structural elements or in industrial uses, we come in presence of various chemical environments, like the presence of water and other things, which through which we come into contact with such interesting topics such as lattice defects and various phase boundaries and precipitate interactions, cracks, and other lattice structures, and stress corrosion cracking and other things likewise. So this is my publication. My major areas of research has been in the hydrogen interaction with defects in metallic alloys in the recent years. Previously, throughout my PhD, I have mostly worked on max phases and magazines, which are also 2D materials, and there also I have studied the interaction of how we can manipulate through various doping and other substitutional elements, the manipulate the magnetic properties and mechanical properties of it. And this is the team with which I have worked with. And thank you for your attention. And now I am open for questions.
So thank you, Poulami, for the nice talk. Now the session is open for question and answers. Maybe first with the students. Questions,
They have understood everything.
or if you have understood everything.
Okay, coming to
the alloy, aluminum alloy, what is the effective component is magnesium. Right? Magnesium. So it is magnesium and aluminum oil and alloy and other defects also. But why not lithium?
Yes, yes. So as I mentioned here, that we have typically chosen one of these alloys because this is the alloy which is mostly and most widely used in the aviation industry, and this is the most high strength alloy right now in the industry. However, it has a lot of advantages to it, which is why it is used in the aviation industry. But it is susceptible to hydrogen embrittlement, and that's why we focus on this alloy for this particular study. But definitely there are other alloys as well, which we have not considered in this study.
Those are alkali.
Alkali, yeah. Aluminium,
Then
lithium.
question will come whether it will form the alloy with aluminum. So,
Mhm. And coming to your question, as you can see, absolutely at the at the intergranular crack, you see this zoomed in portion where there is grain boundary precipitates are being formed here, and the corresponding grain boundary region.
So, Poulami, you showed that with a pin that actually has realism. So, has anything been tried with the pin?
Not yet. We are thinking of. But then there is a problem with tin also because tin has very low solubility in aluminum. Definitely.
Poulami, wonderful talk. Okay. Uh, go to the stress strain law. First.
Yeah.
You see here that basically you guided us from the very fact that the ductility reduced a lot. Now, the whole talk is primarily focused on crack, but where the basically the card is located. You see the so ductility is basically guided by the dislocation. Focus on the research will be done not in this, whether in cracks or
Which is at the end point of it.
which is at the end. So,
But then I felt like this is the reason why we should be interested in hydrogen charging of alloys and then study the further microstructure evolution, right? So since it affects so much, yes, here the effect is seen in ductility, not further. But since there is so much of effect on the mechanical properties, therefore we move on to do, this is what motivates us to charge it with hydrogen and see what is happening in the microstructure level. And therefore, we focus on the microstructural evolution once the material is damaged. Because we are kind of focusing on this part.
Right. So, see, the point is, you were, as a supportive researcher, you did this thing related to back of researchers. But all along from atomistic simulation, in the next leap, you should have focused on the dislocation hypothesis. If this is the, I mean, we know that this, I mean, the dislocation movements are basically primarily responsible for this activity. How does this hydrogen have an adverse effect to have a high damping or dislocation movement? How they hamper with the high presence of hydrogen?
In other words, you basically examine the end product, which is already damaged, which is absolutely interesting and useful information. But on the other hand, the evolution to this damaged condition, that itself is interesting, and I don't know whether experimentally, I'm sure they can actually monitor this.
Yes, they can do experimentally. The problem becomes that such evolution before the damage cannot be done by DFT at least. It can be shown by MD.
Yeah, you do MD.
Yes, it can be done by MD, but not by DFT
No,
actually.
but you do MD and then make an analysis on on the MD structure. That's definitely possible. Of course, you have to do an MD.
Are there any more questions? If not, then let's thank Poulami once again for the nice talk.